Okay, so this is just quickly going through what we did before, some reminders that things we need to know. We need to know standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. We said we can find the molar volume at STP is 22.4 liters. So I don't know what happened to our beach ball, but that it's got marked 22.4 because that's the volume of 1 mole of gas at that temperature. We can also rearrange to find the density of something. So the density is going to be the molar weight over 22.4 because that's the mass in grams of 1 mole divided by the volume of 1 mole. But if I have a different temperature and pressure, then I'm going to use this equation. So you already have that equation in your notes. And then we also rearranged this equation to form this equation. I guess this is in terms of density, moles over volume. But since moles over volume is equal to pressure over RT, from rearranging that, that's how we end up with this one. And then this is the other version of that. So we can solve for molar rate, we can solve for density. I'm going to put this PowerPoint online and there's a couple of example problems. Okay. So if we have the pressure of a gas, oxygen is 0.79 atmospheres, and we want to know what its density in air is at 20 degrees Celsius. We have to remember that we have to use Kelvin, right? So we can't use the 20. So the reason why this says 293 is I added 20 plus 273. And this is an equation I always want to double check on because it's not usually how I do these. So density is equal to molar weight times pressure over RT. That's the equation. Okay. So what's the molar weight of oxygen? So in this case, when I say oxygen, I mean oxygen, the gas, which is a diatomic. So I'm going to count both of them. So it's 32. Okay. So look for the chemical formula on something like that. If you're not sure, do we mean the element or do we mean something else? If the chemical formula is there, use the weight of that chemical formula. Okay, so we use 32, and then everything else in this equation is given to us. We have pressures already in atmospheres, and we already converted this to temperature in Kelvin. So it gets set up like this. And I want you to try plugging that in because when we have two numbers in the denominator, sometimes people make mistakes. So plug it in and make sure you're getting the correct answer on this one. All right, so I got one of those things that's kind of got awkward rounding on it. So how many sig figs do we get? Just 2 because of the pressure. So I got 1.05 grams per liter. And because of that 5, you might have rounded it to 1.0 or you might have rounded it to 1.1. I would typically round to 1.0, keeping it the even. All right, is that what you're getting when you plug it in? All right, if you are getting something that is much larger than that, that is probably because when you're putting in this 293, your calculator thinks you are multiplying instead of dividing. So when you enter it, if you're just doing one right after the other, you would do 32 times 0.79 divided by 0.08 divided by 293. Ways that you can avoid this is some people like to figure out what's the number on top, what's the number on the bottom, and then divide. And then that way you know you're dividing by everything on the bottom. Or you can do divided by and then put in parentheses 0.08 times 293. But remember, your calculator thinks in a line. It doesn't actually think about going through things as a fraction. All right, so let's look at the molar weight since that's the next one on here. So we have the formula on this slide for us. We want to know the molar weight of a gas that we have 3.38 grams and it exerts a pressure of 0.98 atmospheres on a 2.2 liter flask at 22 degrees Celsius. Somehow I left the degree out of there. So units, are we good on grams is grams, so that's fine. Are we good on atmospheres? That okay to use? Yeah. Liters, that okay to use? Yeah. 22 degrees Celsius. No, we got to turn that into Kelvin. This is how I would set it up. And I got about 38 grams per mole. I use 2 sig figs because of my volume there only has 2 sig figs. Now, if I tell you that this gas happens to be a noble gas, which noble gas is it most likely? It would most likely be argon. Now, it's a little bit off from argon. I think when I set up this problem, which I did years ago, I think I had in mind a diatomic. So a diatomic means there are 2 of the same atom that are making up this molar weight. So to figure out the mass of the individual element, what would I do with this 38? Divided by 2. So what element has half of that? Fluorine. Okay. So KMT is kinetic molecular theory, and this is the idea that molecules are moving around, and something about what those molecules are doing is what gives us the properties of volume and pressure and temperature. So volume is how spread they are, out they are, but pressure is about collisions, and temperature is about how fast it's moving. So we're going to look at temperatures in a little bit more detail here. So we said at higher temperatures, the molecules move faster. From physics, we have kinetic energy is 1/2 mv squared. A lot of times we'll use U instead of V because we don't want to confuse it with volume. So this V stands for velocity. But on the graphs I'm going to show you, you'll see a U sometimes. All right. So basically, temperature is a measure of kinetic energy. If the speed or velocity increases, that's going to increase the kinetic energy. The faster the car is going, the more energy it has, and the more damage that happens when it crashes, right? So speed is directly related to that energy. That energy is measured by temperature. Now, when we have molecules, the molecules are not all moving at the same speed. So it's kind of like if we think of an interstate where we have lots of cars. And so the cars are moving. Oh, I have one more thing on here. Kinetic energy also depends on mass, and we're going to come back to that after we talk about temperature. So mostly we've been talking about if I'm looking at one gas, what's going on with the temperature. Later, we're going to say, what if I compare different gases? And then they're going to have different masses, but we'll come back to that. Okay, so we have a distribution of speeds, all right? So on the bottom, this is how fast the molecules are going. So you can think of this as 0 miles per hour. Let's say that's 10 miles per hour, 20 miles per hour, 30 miles per hour. And so very few cars on the road are stopped. Maybe there's a couple at a stoplight. Some of them are going about 10 miles an hour. Maybe this is in a neighborhood. And so some of them are going 10 miles an hour, but very, very few are going super fast. Okay. Molecules in the air are like that too. There are some of them that are moving very quickly. Some of them are moving very slowly. So we have this distribution. Now this almost looks like a normal curve. If you've ever had anything like statistics, you've talked about a normal distribution. In a normal distribution, the tails on both sides kind of peter out very slowly, but we can't go slower than stopped, right? So this doesn't peter out. It just stops here. Here it kind of peters out, and theoretically we could have anything at any speed. It's just very improbable. So our vertical is the number of molecules that are going that speed, or they say the relative number. So think of it as a percent. So all of the area under here is all of the molecules. That's 100%. And then this is the percent that are going just this exact speed. So the most probable speed is, of course, the one where most of the molecules are going that rate. Now, we also have other ways of looking at averages. we're not going to worry about too much the distinction between them because they all fall very close to this. So we have average, we have root mean square is the one we're going to see. So there's a couple of different things, and they'll fall like here and then slightly to the side of it. And the reason why they don't all fall in the middle is because this is not exactly symmetric. So the math for this falls on what is called the root mean square. We're not going to do the math with the root mean square. You'll see it in your book. We're not going to calculate it. But that is showing a particular kind of average speed. Okay, so this is at what they say 1273. 1273 Kelvin. What is that in Celsius? So this is what time we're starting in Kelvin and going to Celsius. So we're subtracting 273. So it should just be 1,000. So this is 1,000 degrees Celsius. That's why they picked that weird number. All right. So when we change the temperature, the curve moves. They all start at 0. But when I have a cold temperature, more of them are going to be going at that slower speed. And when I have a higher temperature, more of them are going to be spread out. Okay. So the 100K, 200K, 500K, those are the temperatures. All right. So I've got purple and light blue for the colder temperatures. 200K is about negative 73 degrees Celsius. So that's pretty cold. 500K, that's nice and toasty. We couldn't live there. 1,000K, that's very high. Okay. So as we spread out the possible temperatures or possible speeds that things can be going, there aren't as many that are going at the slower speed. So that's why the peak is getting lower. Now, people focus too much on how high the peak is. We don't care how high the peak is. What we care about is where the tip of that peak hits this curve. So we're going to drop a line down from just to the side of it, because remember, we're talking about the root mean square instead of the actual peak. But the peak is close enough. And we're looking at where does it hit here. Okay, so the most probable speed here, or the root mean square speed here, is closer to 0. That looks like maybe about 250. As we warm it up, maybe it's closer to 350. As it gets warmer, maybe closer to 600, and warmer still, maybe about 850. Okay, so the higher the temperature, the faster the molecules are going. So since we know faster means higher temperatures, keep that in mind when we switch to looking at different molecules, because we're still going to be looking at this bottom of this graph and seeing where those peaks hit the bottom. Okay. All right. So when we have gases that are moving, they can be mixing, or they can be changing their concentration. So gases are constantly moving. At a given temperature, lighter molecules on average are going to be traveling faster than heavier ones. So this goes back to this equation. If this kinetic energy stays the same, is the same between two sets of molecules, say hydrogen, which we know is really light, and argon, which is much heavier, then in order for them to have the same kinetic energy, which is related to temperature, the one that has a higher mass here has to have a slower temperature or slower speed here. So that's why that relationship happens, okay? The higher the mass, the slower it's going. All right, so here's a graph that looks similar to the one with the temperatures, but instead of temperatures, we have different molecules. What are the numbers in parentheses there? The molar weights, right? So hydrogen, there's 2 of them, so it's 2. Helium, there's only 1, so it's just 4, and they've rounded to whole numbers. Oxygen has a mass of 16, but with 2 of them, it's 32. And so it's showing that at any given temperature, because hydrogen weighs 16 times less than the oxygen does, the molecules are moving much, much faster. And we can tell that because where this peak is left to right is further to the right, right? The peak is around here, which means a faster speed than where the peak is for the oxygen over here. Okay, so light molecules are moving faster, heavier molecules are moving slow. So in the book, they have calculations that you can do using the square root and whatnot. That's why it's called the root mean square. You can calculate how fast they're going. We're not going to do that. We just want a qualitative understanding that at a given temperature, if I look at two molecules, which one's going to be moving faster, that's going to be based on its mass. Okay, so I mentioned two words, diffusion and effusion. Diffusion is the idea that gases are going to spread out. So we know from middle school when we learned about phases that gases fill their containers. So if I have a sample of, say, a perfume or something, and I spritz it here, those molecules aren't going to stay here. They're going to go and fill this entire room. And so diffusion is the process of them spreading out. So in this picture, what I have are two sort of flasks that are joined in the middle, but right now it's closed. On one side, I have hydrogen molecules. On the other side, I have oxygen molecules. And if I just open the valve between the two of them, naturally the molecules are going to spread out into the other container. So diffusion is about both them spreading out, but also how fast that happens. So as we look at this, we're going to see the hydrogen is going to move more quickly into this side where we see lots and lots of the white over on the right-hand side and just very few of the red on the left-hand side. Now, eventually, given long enough, they're going to reach equal amounts on both sides. That's a process we call equilibrium, and they might still be moving back and forth, but it's still going to be equal. But which one reaches the point where it's equal numbers of molecules on each side first is going to be the lighter one. All right, so the calculation with that says that the rate that they're moving is proportional to the square root. So the symbol that I have doesn't go all the way across, but think that it's going all the way across, and then that's the molar weight. All right. As I said, we're not going to use that calculation, but that is just showing you that since we have that on the bottom, remember when you have 1 over something, that's inversely proportional. Okay, so the rate is inversely proportional to the square root of the molar weight. All right, so as an example, think of a container that has both ammonia and H2S is opened. Okay, so say I have it sitting over here, I take the lid off. The ammonia, that's going to make your eyes water. You probably remember smelling that when you were doing your different copper lab because you worked with ammonia. And then you have H2S that smells like rotten egg. So if I open this container, and then we've got Caden way on the other side of the room over there, which one is going to reach him first? So what we're going to have to do is think about what are the masses of the molecules. Anybody remember what the formula for ammonia is? NH3. So we got NH3 and we've got H2S. So we look at the masses of those two and we see that NH3 is 17 grams per mole and H2S is 34. So the ammonia, the NH3, weighs less, which means on average, those molecules are moving faster. So Caden's going to smell the ammonia long before he smells the rotten egg smell of the dihydrogen sulfide. Okay, so that's the kind of question I might ask. It might be a multiple choice question about which gas would get across the room first or is going to go somewhere first, and you're looking for the first one is going to be the lightest one, the last one is going to be the heaviest. Now, effusion is related, but it's slightly different. So effusion is the idea of something escaping its container. So in diffusion, we have these molecules kind of spreading out into a large container. With effusion, it would be like this, and then we poke a hole in it. So they have like, this is your original scenario. All the molecules are over here. And then when you poke a hole, they start moving into this other space. So they kind of needed a middle one that showed all the molecules here and this side empty. But effusion is the molecules moving into an empty space, or at the very least, moving into a space where those molecules hadn't been before. They're going to follow the same rules. But remember, we talked a little bit about, I think we talked about balloons before. Balloons have the polymers, that hold them together, and there's layers and layers of those like spaghetti strand kind of things. But the molecules can kind of work their ways out. So it's kind of like they're moving through teeny, teeny, tiny little holes. So eventually they can escape. And that is a process called effusion. But if you have mixed gases, the ones that effuse, get out of the balloon first, are going to be the ones that have a lighter mass. Okay, so one way that we can use this is to separate isotopes. So chemically, if I have different isotopes of the same element, then I would not be able to tell the difference between them. So a water molecule that has oxygen 16, by and large, behaves the same as one that has oxygen 18. And this is particularly true the heavier they get, because the percent difference between oxygen 16 and oxygen 18 is much greater than the percent difference between uranium-235 and uranium-238. So if we look on the periodic table, we'll see in parentheses the mass for uranium, or do they give a total one? Let's see. I guess there's enough of it that they give the whole thing. So the mass is around 238. Most of the uranium is 238. But there's a small portion that has a mass of 235, and that's much better at fission, which is a nuclear process that allows for energy production and bombs and things like that. So we want to have a higher percentage of that if we're going to make one of those things. So if you think back to World War II, when the atomic bombs were first created, they couldn't just scoop up a bunch of uranium and use it. They needed to pull out just that one isotope. But chemically, those things are going to behave the same. So what they did is they turned it into a gas. They made uranium hexafluoride, and then they used this process where the uranium-235, which was lighter weight, would go through the hole and out first. Now, both of them would get out, but the stuff that they collected was enriched, or a higher percentage uranium-235. So then they take that, the enriched stuff, and do it again. And they would do the process over and over again. So this is why it took so long to get enough uranium in order for them to create the bombs in the first place. If you ever saw the movie Oppenheimer, they talk about the process and how many, they use marbles to show how much of the uranium they have. And it takes a long time for them to collect enough because they have to do this process over and over again. Okay, but we're not going to be dealing with nuclear things. We're going to be dealing with balloons. So let's say we have a balloon that is filled with hydrogen and oxygen. In a few days, is the balloon going to sink or is it going to float? So if it has enough hydrogen, it will float. But then over time, as the gases escape, what might happen to it? So before we answer that question, this is an image from your book of two balloons. And on the left, we have one that has helium in it, the one that's reddish orange, and the blue one has argon in it. So argon's heavier. And then they say 12 hours after being filled, they took a picture again. So this was helium and this was argon 12 hours later. Which one has changed the most? The helium has changed the most. The lighter weight one has escaped the balloon faster. Okay, so to answer our question, we have to think about what's escaping, and then we have to think about, well, what's still left in the balloon and what's going to make that happen. So this is like moving from a direct question, which one escapes faster, to an application question, a little bit higher level thinking. So which is going to escape faster, the hydrogen or the oxygen? Hydrogen is going to escape faster. What's left behind? Oxygen, right? So there's still hydrogen in there, but it's much more concentrated in the oxygen. Oxygen's heavier, so the balloon is more likely to be sinking, less likely to be floating in the air. All right, and so again, looking at our graph, we can see that the oxygen is moving very slowly while the hydrogen is moving very fast. So it can get to those holes and escape much faster. And then follow this up. The remaining gas will be more dense. Okay.